So what I thought would be a good idea would be to go over some of the things that I raised in the latest pedagogy from not exactly the same way, although I will go over some of the stuff that I did in the pedagogy, but I think people have had a chance to look at it. Plus, we've done some classes on it here several times. I think I tested out some of those ideas on you guys several times. But I wanted to actually sort of delve in a little more into the ontological question that Lynn pointed to in his little preface that he made to the which he added to it, which is on this question of the quantization of space, quantization of space-time. And this is a concept which is usually associated with modern science, this idea of a quantization of space. And I'll describe in a minute how that comes up in modern physics. But this is something really which goes back much further, back all the way to the pre-Euclidean idea of the Pythagoreans and spherics, which is what Lynn was really emphasizing. And Plato raises this whole question in the Timaeus dialogue, and it's also raised by Riemann in the habilitation paper in using somewhat different terms, but it's the same idea, which is one that's very critical for really understanding economics. And as Lynn pointed out in the question of in his preface, it really boils down to this question of metaphysics. And it's from metaphysics that the solution to a lot of these problems are resolved. That is, if you're dealing with questions not only in physics and science, astrophysics, microphysics, biology, but also social sciences, especially economics, but also politics. You know, we had an overview a minute ago on the political crisis and the situation with Rohatyn, and one thing that comes to mind, right, that everybody brought up is, you know, why is this guy Rohatyn? How does Lynn know that this guy Rohatyn and his role is the crucial flank that we have to hit on right now? Because you wouldn't know that on the basis of sense certainty by looking at the political situation. If you look at all the players and everything that's sort of out there in the front edge of all the political debates right now, this issue that, or the way in which the strategic question that Lynn has posed on this question of Rohatyn would not be recognizable. So what is it about Lynn's method for understanding politics that enables him to focus and to make this kind of key strategic decision as to how to deploy effectively what are obviously relatively scant resources for maximum effect, because we have to have maximum effect in order to change history. We have to win this war. This is not a war that we're fighting because we want to fight a war, we want to get into a fight with the establishment, and we think it'll be a good career move or something like that, right? This is a war that has to be won because the consequences of losing are, a dark age, or the collapse of civilization. So, and yet we're having to fight this war against an enemy which appears to have much more resources than we do, and obviously on the surface they do. And we have to, with our relatively scant resources, be able to effectively defeat this enemy. Now, that's not the first time in history that a group with very scant resources had the responsibility of defeating a much larger and superior enemy from the standpoint of resources. Obviously, the American Revolution is the perfect example of that. where from the standpoint of resources, military capability, the American revolutionists had much less available to them. And what they deployed was not simply the military capability that they did deploy, which is you can study from Washington's military actions, which people can study at some other time. But what they deployed, what Washington really effectively deployed, and what Franklin effectively deployed, and in the American Revolution was, in a sense, a metaphysical question, not a physical one. They deployed the principle that was enunciated in the Declaration of Independence and the concept from which those principles that were enunciated flowed. That is, they understood this, as Stephanie said, right? The issue here is that this is not new, what Rohatyn is pushing. This goes all the way back to the 10th century. This is, these are people advocating going back to a dark age. And what we have to mobilize is something far superior to that. What we have to mobilize to bring to bear on this situation is a superior quality of the human mind. And that is something that one has to actually get to know. And that's the issue here, which is from the standpoint of this question of metaphysics and the idea of quantization of space, is really getting to know a certain capability of the power of the nature of the human mind, not from the standpoint of the mind as some individual human mind, but this social process of which, as Lynn has emphasized both in the capital budgets paper as well as the some of the other things that he's written recently, where he's emphasized not only the effect of society on the individual, but the effect of the individual on society. That society creates the potential for the individual to be able to do what he or she can do, but the individual also changes the society, which changes that potential. Lynn, of course, is the perfect example of that, right? Who is the product of a certain, is affected by, as he's emphasized on this question of generations, the generational question, and how this shift in the Roosevelt effect of Roosevelt and the experience of the World War II generation, and as he talks about his family history going back to 200 years and his relation to the American Revolution from that standpoint. But Lynn also is changing the society, which he's being affected by. Right? He's actually intervening and changing the social dynamic, which he's been doing for the last 40 years, and increasing effectiveness. And you see it right now in the fact that Lynn intervenes on this question of Rohatyn, and it begins to shift the entire politics of the world. Or another thing which wasn't brought up in the briefing, but which is also very significant, is the thing that Lynn talked about with Prince Philip. That was in the Sunday briefing. And this question of how this retrospective acknowledgement by Prince Philip that his family was big supporters of the Nazis. In fact, 3 of his sisters were members of the Nazi Party. Mm-hmm. And that he acknowledged that, his family was favorable to the Nazis because, after all, things got better. Certain things were good that happened under the Nazis. The trains ran on time, and there was a social order instead of the chaos of the Weimar Republic. And many people thought this was very good. And of course, who knew what eventually would happen with the Nazi regime, right? Of course, the article points out that Prince Philip did fight in World War II against the Nazis as a member of the British Army. But what Lynn pointed out, which is what's important, is not that Prince Philip acknowledged that his family were Nazis. Lynn has acknowledged that, and that's something Lynn's talked about, and you could say on one level, well, okay, this proves Lynn was right. He said that Prince Philip was a Nazi, and now he's come out as Nazi. But that his acknowledgement that the oligarchy at certain times in their history found Nazism and fascism to be a useful tool to deploy in their ends to maintain their empires. That's the level at which you have to understand the political dynamics that are going on here. So that requires developing a certain competency in understanding this question of metaphysics, which of course is not what, you go to the internet and you look up metaphysics and you find, people who stare at rocks and put crystals under their beds and this kind of thing. And that's not what we're talking about with metaphysics, right? What Lynn is focusing on metaphysics, he said only the idiot would think metaphysics is something outside the physical universe. Lynn's talking about this idea of the Pythagorean idea of spherics, and interestingly enough, how this comes up under this rubric of the scientific puzzle, so to speak, on the quantization of space-time. And as I indicated, Plato brings this up in the Timaeus with respect, for example, to the 5 regular solids, that the image of the universe as the idea of a spherical universe is the image that comes to mind, that the mind constructs with respect to thinking about what is the form of the idea of the universe, the concept of the universe as being universal, which is, I remember, several years ago, Lynn used to get a lot of questions. Well, what do you think about the possibility of other universes? This is very popular today, and not only in science fiction, but also in physical scientists and cosmology and so forth. They talk about the possibility that there are parallel universes.
Black holes.
Yeah, they're on the other side of black holes or something like that, right? The existence of parallel, which is just a crazy idea, and it's because universe means everything. That's what the word universe means. It's a word which signifies the existence of the all, right?
Why can't we have 2 alls?
You're right. Well, then you'd have a third all, which encompasses the 2. So now we get to our question of the transfinite that we were talking about earlier, right? But yeah, that's the idea, right? This is the paradox that Russell tried to use to this is where this thing came with his discussions with Franzelin, because the paradox comes up when you're thinking about the transfinite is what is the transfinite of all possible transfinites? Well, if you think about the way transfinites are constructed, if you had a transfinite that was transfinite with respect to all other transfinites, then that would imply the existence of a higher transfinite. So, in effect, Russell would argue that the idea of the transfinite is itself a bad infinite, because it has no bound to it. And that sort of gave Cantor a little bit of difficulty, which is why he got into this whole, he had some difficulty when he tried to deal with this question from a formal mathematical standpoint, because the issue, it's the same paradox that Lynn has often pointed to that Philo raises against the Aristotelians on this question of perfection. If the perfect universe is, the perfected universe is something which has achieved the greatest possibility of perfection, then it's imperfect because it's not capable of changing. Because if it's capable of changing, then it's capable of becoming more perfect. But if it's capable of becoming more perfect, then it couldn't have been perfect in the first place. So, but that's an Aristotelian construct, because it assumes that perfection is a fixed state, as opposed to the state of the possibility of the maximum possibility for self-perfection. Self-perfectibility is the highest state of perfection. So, and this is what Plato is talking about in the Timaeus. right? That you have the universe, which is self-developing, self-bounded, which is why he gives the disclaimer in the beginning, right, of the Timaeus, where he says, okay, now I'm going to start, you ask me what I think, but I'm going to have to use words to express it. So when I use words, I'm describing an image. And when I'm talking about an image, don't mistake the image for the real thing, because the real thing is something that is beyond the domain of sense perception. So then he starts talking about the idea of the sphere, the spherical image of the universe. But then he raises this question, which I think some of you have gotten into who've been working on the Mysterium, and you constructed some of the 5 regular solids, which of course is one of the first discoveries of the Pythagoreans. And it goes back to the Theaetetus and Theodorus, but also much further back, because we actually have archaeological evidence of these regular solids being carved into spherical stones that date much, much, much earlier than the Pythagoreans. Because this is a universal discovery, that there are 5 and only 5 regular solids. And Plato raises this is why we call them the Platonic Solids, because this is the first written record of these solids is in the Timaeus. And the idea of the 5 regular solids is already poses this paradox, which modern physicists would call the quantization of space-time. Because you have this sphere, which is everything. It's perfectly continuous and perfectly smooth, and yet there's a bounding condition which is not evident in the visible form of the sphere itself. You can't, it would appear, from the visible form of the sphere itself, there's nothing that tells you that you can't divide that sphere into an infinite number of equal parts. That there's some principle that restricts you from being able to divide the sphere into anything other than 5 and only 5 regular solids. Now you can go through several constructive proofs of that, both from the way Kepler does it, which is a reflection of the Greek idea, by constructing the polygons and seeing which ones can form solid angles, or from the more advanced way that Gauss does it by investigating the nature of the curvature of the sphere. But nevertheless, you get what is in effect a quantization of the spherical surface. That is, we do not live in a universe that is as that universe is described by Euclid or by Aristotle. That it is an empty, we start off with a tabula rasa, an empty space in which anything can happen, and the things that happen because they happen to happen. Right? The shit happens theory of metaphysics. Right? But which is the and of course this gets more sophisticated in the Copenhagen interpretation of quantum mechanics, because they say that the reason why these things happen, even though anything could happen, is because these are the most probable things that could happen, right? But well, let's take this question of probability for a second and just take a little digression into this, right? Because take the probability. You flip a coin 10 times and you say, well, there's a 50-50 chance it'll come up heads or tails. But if you flip it 10 times, it probably won't come up 5 heads and 5 tails. It's probably more probable it'll come up 7-1, 3 to another, maybe 9-1, right? In 10 flips, it's just as likely to come up 7-1, or 7-3, or 8-2, or 4-6, or something, as it is to come up 9-1, right? If you flip it 100 times, you'll come up a little closer to 50-50, but it's probably, it might be 60-40, it might be 45-65, right? If you flip it 1,000 times, you'll get closer and closer. But you'll never get exactly to 50-50. And in fact, the more you flip it, the more other factors will come into play that will put a bias into the flipping, like the wearing out of your thumb. The fact that your thumb becomes tired and you might start flipping it a little bit differently, or the fact that the more the coin starts hitting the ground, it'll start to get worn off in certain places and become unbalanced. It might rotate a certain way. All these various factors which will come into play, which will start to create a bias. And you'll see it isn't exactly 50-50. It isn't that anything can happen, but what happens because of certain concatenation of a whole series of physical circumstances which produce something happen. There is no such thing as empty absolute space. And that's really one of the crucial questions of metaphysics, yeah.
So are you saying that there's no such thing as random distribution?
Absolutely. In fact, the idea of random distribution is a human idea. It's not something that's ever been discovered in the physical universe. Right? And man is incapable of producing a physical process which is absolutely random. Well, the computer does it by a physical process, right? I mean, it has gates, and you're pushing electrons around according to some principle, which you assume is random. And as soon as you construct a computer chip, which is supposedly dealing with a random process, it never produces a random number generator. So, but the computer it's a physical process. It's a counting machine. It's no different. The modern digital computer is no different than Leibniz's calculating machine, except instead of gears, it uses electronic switches to turn off and turn on instead of a gear, instead of a mechanical switch. So that's all. That's the only difference. But it's a physical process, right? And but this concept of the existence of physical space-time as opposed to absolute space-time is the first concept of man, not the other way around. And the introduction of the idea of absolute space, of Euclidean absolute space, is a sophistry which is introduced to try and enslave people. It's like this question of free trade. It's a good example of how the same type of process works in terms of social process. There is no such thing as an unregulated market. The economy is going to be regulated. It's either going to be regulated by, as Rohatyn says, and Schultz, private enterprise, private financial interests who are going to regulate it, or it's going to be regulated by governments, which are constituted among men in order to promote the general welfare and to secure the blessings of liberty to ourselves and our posterity. Or it's going to be regulated by whatever governments there are, solely for the purpose of, as instruments of private financial interest, in the same way that the feudal kings were instruments of private feudal lords. The bullshit they teach you in history about the Magna Carta being the introduction to democracy, because it provided certain, took away power from the king and put it in the hand of the House of Lords and created the House of Commons. Of course, the House of Commons was not commoners, but these were bankers, right? If you look at the whole Venetian banking system, it was private Venetian bankers which determined what kings and queens and emperors could do. There's the famous case of Johannes Kepler, who was the imperial mathematician. He was appointed to be the advisor to the emperor of the Holy Roman Empire. And he was promised a salary. But he never got paid that salary. Why? Because the emperor didn't have the money. How could the emperor not have the money? Because the bankers didn't loan the emperor the money. So who had the power? The emperor? He was the sovereign of the Holy Roman Empire. But he was beholden to private financial interests, the private banks. Private financial interests which were dominated primarily in Venice. So there is only a regulated economy. The economy and economic relations and social relations among human beings are regulated. And they're regulated not by human beings. Human beings are the instruments of the regulation, but they're regulated by principles under which the human beings act. Metaphysics, metaphysical principles. And those metaphysical principles are principles about the nature of man. They're the most fundamental metaphysical principles. They're the principles of what is the nature of man. And, either you have the conception of man, the Pythagorean, Platonic, Socratic conception of man, that man is the creative powers of man, and that man has this immortality to his nature, or you have the Lockean, Mandevillean, Aristotelian idea of man, that man is basically, a bag of bones and enzymes, and whatever thought we produce is simply, if there's any coherence between thought and the universe, it's purely accidental. It's not a determinative process. Now, so the point is, so you get to this question of there is no absolute free market. There is no absolute empty economic space. This is another expression of this idea of Euclideanism or Newtonianism. In fact, Lynn made a joke the other day, which he said, he's discovered a new fundamental particle which destroys spiritual effectiveness. It's called the Newton. The Newton. The Newton. It's the fundamental particle which destroys spiritual effectiveness. The Newton. So these are, and it's important to sort of just keep rethinking that because you get into this, because we live in a society which accepts this false idea of a Euclidean empty space as being axiomatic. People think that you're deviating from this concept by imposing on this space some type of structure, when it actually is the other way around. The idea is that the idea of Euclidean space, of absolute space, of some Newtonian type of idea of absolute space, is a construct which is imposed on the experimental evidence and the ideas which arise out of that interaction of the mind with the physical universe about the quantization of space. And this, so this comes up, as I gave one example, on the question of Kepler. The Plato and the Timaeus. But it also comes up most dramatically in the question of Kepler, and you see this again with this question of Kepler versus Newton. Because for Kepler, the planets aren't anywhere. There isn't an empty space in which you could have 20 planets or 10 or 5 visible ones, right? There isn't just a arbitrary possibility for anything to happen, but that there is what there is, which is 5 for Kepler, which is that there are 5 visible planets, and these 5 visible planets happen to be where they are because there must be some principle. And Kepler recognized that principle must conform to a principle which is cognizable, because God would not have created man with the power of cognition were it not for his desire that man would discover the principle of creation and in that way continue God's creation. And, yeah, that God would not have created man with the power of cognition were it not for the fact that God intended for man to be able to recognize the principles of the physical universe, and thereby gain a mastery over those principles, which is the way God's universe is one that is the most perfect, because it is self-perfecting. It has a principle in it which perfects the creation. And that principle is the creative powers of man, and the fact that the creative powers of man are efficient with respect to the physical universe itself. Right? There isn't an empty space, right? And this is the argument Leibniz has against Newton. That if you assume that there's empty space, as Newton does, there's an absolute space, which he calls the sensorium of God, space-time, space and time. And then against this backdrop in which anything could happen, what happens, happens. And of course, Newton is quite explicit. He says, hypothesis non fingo. I don't make any hypothesis as to what gravity is. I'm not saying what gravity is. I'm just describing its effects by this mathematical law, which we call the inverse square law. And this inverse square law is, this inverse square law, as Leibniz points out, you could construct, again, this idea of multiple universes. You construct a solar system in which all kinds of things happen that don't happen in ours. Planets moving. Why do all the planets move in the same direction? Because under the inverse square law, you get the same equation where the planet's moving, around the sun this way or around the sun the opposite way. But all the planets rotate around the sun in the same direction. Why do they all rotate in the same plane? Because according to the inverse square law, if that planetary orbit were anywhere, right, in that plane, you would get the same calculational effect. The inclination of the orbit is independent of the inverse square law. So these this is the question Leibniz raises. For Kepler, the solar system is, as he points out, harmonically ordered. He uses the term harmonic. And you see this same thing with respect, for example, with music. Music is as the music theorists start from an idea of an absolute abstract musical space in which you have any possibility of tones. You can do anything you want with these tones, and we just happen to prefer some arrangement versus another arrangement. But if you listen to, for example, Indian music, you have, quarter tones, and you have a 24-tone scale or a 48-tone scale. You could stick in as many tones as you want. You can put all kinds of combinations together. And there's some existence, some absolute space out there, right? In which any music is possible. We just happen to prefer some music over another. But that's not the way music. This is again a false construct, because that's not the way music is created. Music comes out of language, and every language has a certain characteristic musicality to it, has a poetry to it. And you have various vowels and pitches and musicality with respect to the language, and that musicality suggests a musical or is constrained by what we recognize in its more advanced form by the bel canto principles of well-tempered polyphony. But these are functions not of some abstract thing, but there are certain principles, as you know from the singing. You can't just sing anything you want. If you don't sing according to the principle of well-tempered bel canto, and you don't have control over your voice from the standpoint of bel canto, you can't actually sing a well-formed idea. The same thing with your language, right? language has certain grammar constructions in it, which the poet and the writer violate through irony, right? But if you do not use that, if you're not conscious of the language structure, then you have a difficult time putting the sentence together, in which an idea gets communicated from yourself to someone else, which is, as I've often said, which is why people in modern parlance today punctuate their sentences numerous times with "you know," because they're not sure that what they're saying is communicating an idea. So they have to keep saying, "You know what I mean? You know what I mean?" Because they're very unsure that what they actually mean could possibly be communicated to another person. Because they're aware of the weakness of their control over the language. Right? It's the same thing with the bel canto singing. That you can, if you don't have control over your voice from the standpoint of bel canto, then you can't actually communicate a polyphonic composition, such as the Jesu Meine Freude or the Ave Verum or any of these kinds of things. That's another example of the idea of quantization. So there's certain principles. Let's go back to the astrophysical example. So in the case of the planetary orbits, right, this astrophysical quantization is a reflection of the physical process out of which the solar system as we know it today evolved. In other words, what's embedded, the harmonic characteristics of the solar system as Kepler observed them, express the principle out of which the solar system was created. The planets were not just plopped down in empty space, like ping pong balls. Right? There was, as Lynn has discussed, which is generally accepted, or becoming increasingly accepted by modern scientists, that you had a rotating, spinning plasma disk, which then separated out into these rings, ionized rings, which were the harmonic locations, the equivalent of standing waves within this rotating plasma disk. You had the equivalent of these standing waves, which form these rings, which then condensed into what became known as into the places where the planets are. And so that's why the planets are where they are. Not because the planets were plopped down like little ping pong balls in empty space, but because a physical process produced the solar system, of which the artifacts are the rotating planets, and that's why they're rotating in the same direction. And that's why you have this register shift between the inner planets, which are small and solid with a few moons, and the outer planets, which are gaseous and large with many moons. You get a shift in the actual material composition of the planet. The same thing, you see another example of this concept of quantization if you look at geology, which is very important for the work that we're doing on nuclear energy, nuclear science. Ida Nodak, one of the founders of nuclear science, who Jonathan talks about in his book on nuclear energy, had this principle of the omnipresence of all the elements, that if you take any part of the Earth's crust, you can find in it traces of the entire periodic table of the elements, right? So they're everywhere. You could take a gallon of seawater and you could find traces of all 92 elements in that gallon of seawater if you could do the chemical analysis that would be able to extract out such minute quantities, which you probably could right now. But when you look at the Earth's crust, there's not a homogeneity of the distribution of the elements. They actually are concentrated. You have concentrations of these elements: iron deposits, bauxite where aluminum is concentrated, pitch blende where uranium is concentrated. Different kinds of concentrations of these elements.
Are those places, do you think?
Yeah, well, places on the Earth's crust, like the iron deposits in where you have iron mines and in coal mines, and iron in Michigan and
So pitch blende?
pitch blende. No. Pitch blende is a mineral of which uranium is a high concentration of uranium. Just like bauxite is a mineral of which has high concentrations of aluminum in it. So you mine the bauxite and then you process the bauxite and you extract out the aluminum from the bauxite because it has a higher concentration of aluminum in it than there is in the dirt that's right outside your house. But there's still aluminum in the dirt outside your house. So obviously, if you have more advanced technologies, then you can begin to extract the elements out of these more diverse areas. But you get this, you don't have this, the world is not one big giant mush where everything is distributed, well mixed up into this empty space. There's a concentration. What is that a reflection of? Well, from the standpoint of Vernadsky and from the standpoint of a lot of modern evidence, this is the result of a biotic process, of the effect of life on the planet. That the concentration of minerals at various places reflects the effect of a living process. And there was a discussion recently, because the group that's out in Leesburg right now doing the animations, looking at this question of the aquifers. And how do these, what's happening with this water question? Because Lynn's raised the question of the fossil water. That the water that's in these aquifers was deposited in these aquifers by the last ice age, around the time of the last ice, with the receding of the last ice age. And this fellow from Australia has this theory that the aquifers are not charged from rainwater, which, when you look at the hydrologists, they acknowledge that the idea of the recharging of aquifers by rainwater, it contains a whole lot of assumptions. There's no actual physical evidence that that's happening. And he says that it's not happening at all, that the recharging of the aquifers it comes from below, water bubbling up from inside the earth. But Lynn said, no, that's not the way it works either, because this is the result of these aquifers are the result of a biotic process. You have to look at the interaction of life and go back and look at what was the characteristic of living processes as the ice ages, the glaciers began to recede. So that's the direction you have to look at, right? Because when you're looking at the Earth, you're looking at living, non-living, and cognitive processes interacting. So you can't look at something like it's just like with the solar system. The planets are not equally distributed. The planets are distributed in an unequal way. This is one of the problems Kepler has in the opening of the Mysterium Cosmographicum, because if you take the orbit of if you take the relationship of Mercury to Venus, Venus to the Earth, and you continue that, there should be two planets between Mars and Jupiter. But there's none. Or there's the asteroid belt. If you take the relationship of Saturn to Jupiter and you continue that inward, there should be one planet between Jupiter and Mars. And there's none. There's just the asteroid belt. So there's not an even distribution of the planets. There's an uneven distribution of the planets. It's not arbitrary, but it doesn't conform. It doesn't conform to some simple numerical function, some simple function, or some simple algebraic function, or some simple process. And Kepler talks about in the Mysterium how he wasted a whole bunch of time looking for such a thing. Right? But he finally found it by looking at the 5 regular solids. And the ordering of the 5 regular solids that he discovers is an ordering which is not an obvious ordering. It's not the same one Pacioli has. It's a fairly sophisticated one. Right? So when you look at the physical universe, you find that this is the nature of things, not the other way around. Right? And this also was one of the and Riemann. Riemann discussed this in the habilitation paper. In a couple places, he indicates the importance of this idea, where he discusses that this difference between the continuous and the discrete manifold. In a discrete manifold, you have just objects which you can measure by counting them and describing their attributes. In the continuous manifold, the measurement has to come from outside. And that if the physical universe is discrete, then all there is, that is the visible object of space, then all there is to count them and describe them. But if the physical universe is not discrete, then the measurement of the discrete must come by measuring the forces acting continuously on the discrete from outside. And then Riemann emphasizes that that you cannot assume that the way things appear in the visible in the domain of observation, in what we sometimes refer to as the macroscopic domain, extend or continue in the very small and the very large, in the microscopic and the astrophysical domain. And he also, I put this quote in there from his fragments where Riemann discusses this question from the standpoint of science, of the general principle of science, that you make certain assumptions by looking at investigating certain things on a certain level, either in astrophysical or microphysical, and then as your measurements become more precise, you have the ability to discover changes in principles which otherwise would not be visible. That doesn't make your previous conclusions false, but they have to be consistent with the changes. There has to be a reason. You have to discover a reason for why it changes, and this becomes the issue during Riemann's lifetime, but especially following it, when you have the question of the anomalies in the observed experiments in the macroscopic domain, which indicate the existence of microscopic phenomena, such as the Ampere and Weber experiments, which indicate the existence of microscopic phenomena which are different than the way things appear in the macroscopic domain. Most notably, Weber's hypothesis that in the microscopic domain there's a shift in the Coulomb effect from like charges repelling to like charges attracting, which was later confirmed by our investigations of the atomic structure.
What is the effect? What is it called?
The Coulomb effect. Coulomb, yeah, he developed the hypothesis that electrostatic charges behave according to the inverse square, with the exception that like charges repel each other according to the inverse square, and unlike charges attract each other according to the inverse square. This was just an elaboration of Franklin's work, but Franklin was really the first one to realize that there were two types of electricity, positive and negative charges, which is already knowable, already empirically discoverable with respect to magnetism. by just experimenting with a magnet, and you can find that if you have two magnets and you put them together one way, they attract each other. If you put them together another way, they repel each other. But what Weber said was that in the very small, that process reverses. Instead of the like charges repelling, they start to attract. He didn't have any. This was a hypothesis on his part. Now, another experimental evidence, and Kepler had also said the same thing, that on the astrophysical domain, he said, this space is quantized. Space-time is quantized. It actually acts according to a harmonic ordering principle. That's why the solar system, the planets are where they are, and the relationships among the elliptical orbits conform to these musical tones. And he also hypothesized the same thing in the microscopic domain, which he discusses with the snowflake paper. He uses the snowflake evidence. And why does a snowflake always have 6 points? Right? And then he uses the thing with the bumblebee. The bumblebees don't make a big blob of honey. Right? Honey is bee vomit. Right? That's what it is, right? I don't want to gross anybody out, but outside of man, this Disney, this National Geographic Disney nature movies, they really give a false impression of nature. Outside of man, nature is mostly sex and violence and eating and excreting and sex and violence.
Bill does this great thing with, he talks about these cute baby turtles.
Yeah.
Oh yeah, the ones that die before they get to the shore.
Yeah, that they're just hatched en masse, and then when they all hatch, it's a massacre.
Yeah.
They survive.
It's uncivilized, right? But the point is, the bees don't just puke up a big massive glob of nothing, right? They make these nice little rhomboids, these hexagonal chambers, in order to store their honey in. Right? And he makes the hypothesis that this is an ordering principle. This reflects a quantization of space because of the close packing of spheres. Yeah.
Where was the first use of the ratio?
Well, it comes up. Einstein is the one who uses it. Einstein and Planck. In that form. And it comes up in Planck actually in a way that reminded everybody of Kepler. Because if you take the experimental evidence that Planck was dealing with, it had to do with the relationship between light and heat. Radiation, right? Because if you think of heat, radiating heat, right? You have heat, it radiates continuously. When you have a body radiating, that's say a piece of metal which is heating up, like the coils on your stove, right? They heat up and they radiate heat continuously. And the heat, there's not a cool spot and then a hot spot and then a cool spot and the heat radiates. If you put a thermometer anywhere in the region of space around the heat, you'll get a temperature. Same thing with magnetism, right? If you have a magnetic field anywhere outside the magnet, you move a compass around, the compass will move. There's nowhere in that region where there's not a magnetic field. So it appears to be a continuous process, which has a certain gradient to it, but it's a continuous process. And the same thing with light. And if you look at the rainbow, in the rainbow you have the colors of the rainbow, starting with red, ending up with violet, but they're not. They change, but it's a continuous change. The red, there's not a sharp line between red and orange. There's not a sharp line between orange and yellow. It gets a little more yellow and a little more. These colors sort of morph into each other. So when you look at there's say a piece of metal that is being heated. It gives off heat. It absorbs heat, right? And it gives off light. And this is a non-perfect example of what the idealized case is called a black body, the so-called black body radiation. And black body radiation is the idea of a body in which it's self-contained and all the heat that's radiated out of it is also absorbed. It radiates as much as absorbed and eventually reaches a point of equilibrium. And if you could poke a very tiny hole in the black body and see what wavelength the light was coming out of it, the light coming out of it was emitting, there was a red light or yellow light or blue light or something, that would show you the rate at which the relationship between the heat and the light. Now this is a simpler, more intuitive example of this idealized idea of a black body is, say, a piece of metal, a piece of iron, which as you heat up is absorbing the heat and radiating the light. And at certain temperatures, it radiates out light of a certain color, such as red. And then you heat the temperature up and it starts to turn a little yellowish. And then you heat it up some more and it turns more bluish. And then it gets sort of a whitish blue. But if you do a careful investigation of the colors that are coming off that light with a spectroscopy, you run it through a prism and you break out the different wavelengths of the light that are coming out, the different colors. You find that actually at every temperature it's emitting every color. And however, at each temperature there's a certain color which is emitting, it's radiating with the greatest intensity. So in the lower temperatures, for example, red, it's radiating all the colors, but the red it has the greatest intensity. And as you increase the temperature, so it forms at any given temperature there'll be a little curve, and that curve will reflect the wavelengths at that temperature. You have a temperature line, then you have the wavelengths at that temperature.
And with white, they're just
well, it never really gets white. It gets more bluish, and if you could continue to heat it up and it didn't turn into a gas, it would, radiate X-rays. But that's the other problem, right? Why does it? There are two things that happened here, right? One is that at each characteristic temperature, there's a peak in the intensity, and then it drops off. So that temperature, then you heat the temperature up, you increase the temperature, and the intensity of the light, the wavelength of the light that the most intense shifts towards the higher frequencies. But then it drops off. It doesn't continue that if you increase the temperature, there's an infinite increase in the frequency of the light emitted. You get this dropping off.
How do you measure intensity without you see it.
Well, you can get instruments that will measure the intensity of the light, the brightness of the light.
Brightness of it?
Yeah. You can measure intensity by exposing the light to photographic paper and seeing how it. I don't know exactly how they did these different experiments, but that's one way you can do it. They're different. It's indirect measurements, but there are these very careful experiments done, very careful experiments to produce these measurements. And the question was to come up like Kepler's problem of trying to come up with a principle that ordered the planets where they were. And if you had they had the same problem that Kepler had, that if you came up with a certain relationship that ordered the relationship between the distribution of temperature and light from the standpoint of the lower temperatures and in the higher frequencies, it didn't hold with the higher temperatures and the lower frequencies. So Planck, just purely trying to come up with this mathematical expression, realized that if you assumed that the light and heat relationship was not a continuous one, but that there was a very small number, which I think is 6.235 times 10 to the minus 23. It's a really tiny number, right? That this was a quantum of action, as we call it, a quantum of action. That that would then explain this relationship as to why, as you got to, and that the frequency, the energy, was the relationship between the energy and the frequency was proportional to this constant that didn't change. So as the frequencies got higher, the energy, the frequency multiplied by this constant, became big enough that you got this dropping off effect. I mean, one intuitive way, which is often used to try and explain this, is to think about if you were in a swinging, you go on a swing, right? And if you just sort of are doing a sort of relaxing swinging back and forth, your swing goes up maybe a foot off the ground, back and forth, right? And it takes a certain amount of effort to keep your swinging going 1 foot off the ground. And if you increase the effort a little bit, you can swing 1.5 feet off the ground, right? If you increase it a little bit less, somewhere in between the two, you can increase it 1.25. If you put a little more, you can swing 2 feet off the ground. If you put even more effort, you can go up to 3 feet. And you have an intuitive idea that you could, with a continuous variation in the amount of effort you're putting into your swinging, swing to whatever height you want it to, all a continuum of heights, any height off the ground you want. But the way it actually works in this case would be that you're swinging, say, at 1 foot off the ground, and you put more effort into it, and you still swing at 1 foot off the ground until you put a certain amount of effort into it, until you increase the amount of effort a certain amount, and then you swing to 2 feet off the ground. But you're either at 2 feet, you either are putting enough effort into it to swing at 2 feet, or you're putting less effort in which you swing at 1 foot. So there's a continuous amount of effort to swing at 1 foot, but then once you cross over a certain boundary, you're now swinging at 2 feet. And then you put in some more effort and you jump up to 3 feet, but nowhere between 2 and 3, right? That's what Planck's constant implies with respect to this relationship of energy to frequency of light emitted, heat and light. So he proposed this idea of the quantum of action. Now, you had other experiments which indicated a similar type of quantum of action, such as with light. One is the experiments of Fresnel and Thomas Young and so forth that indicate light acts as a wave. And the other was the so-called photoelectric effect, where if you shine light at certain metals, you can detect electric currents coming off. And that's not characteristic of a wave, because if you increase the intensity of the light, the number of electrons coming off increases, but not the force with which they come off. That increases only with an increase in frequency. And so Einstein, in the paper he actually won the Nobel Prize for, said that light, the only way this can be explained is to assume that light in this case, is acting as a stream of particles. Not a continuous wave function, but a stream of particles. And that those particles he called photons. So this started the whole idea of quantization as a concept that the universe was quantized. And more experiments indicated this, that there was a certain quantum of action. Now, but you have other examples of this. For example, just think about the periodic table of elements. The periodic table of elements, everybody has the image of the table in their chemistry department, right? The chart, and they say, okay, helium had two protons in it and 2 neutrons, and you think of these little hard balls, and that's why it's discrete like that. But that's not how when Mendeleev grouped the elements according to similar chemical properties and compared that with with the atomic weights, and he showed this periodicity. But there were certain anomalies, because in the Mendeleev table, potassium and iodine are reversed. They're in the wrong column. They're grouped with elements which don't have the same chemical relationship. So then there was, if you look through the spectroscopy experiments, you take these different elements, you heat them into a gas, and you analyze the frequencies of the radiation coming off of the gas, especially the X-ray radiation. And it comes off in discrete lines. And you look at those discrete lines, and they jump by a discontinuous amount, which this guy Moseley indicated were what he called atomic number. When he called it atomic number, he was referring to the changes in the spectral lines of the X-ray spectrum. It wasn't until after Rutherford discovered the existence of the proton and the mass of the nucleus, or the number of protons in the nucleus, that this atomic number, became associated with the number of protons. So that's the point to look at here, which again, people should do more work on this question of physical chemistry. But the point to look at here is that when you actually do the experiments, the physical experiments, the characteristic of the experiments indicate that you don't have continuous action in the very small. It's much more like Kepler's snowflake paper, right? That when you look at very small things, they have a structure. They have a very definite structure. And that structure becomes more and more, obviously, more and more difficult to discern the smaller you get. And so when you get to a very small region, the Copenhagen, people said, well, we can't really discern, we can't see the 6 points on the snowflake. But we can see the shape of the ice crystals that are formed by a whole bunch of snowflakes packed together. So what we can do is assume that we can say that this macroscopic effect is the effect of the microscopic domain of a certain characteristic of action in the microscopic domain. But that the Copenhagen interpretation explains as simply the most probable outcome, that anything really could happen. but that what does happen is simply the most probable outcome of what we observe is the most probable outcome of anything that could happen, right? So how do we actually begin to solve these kinds of problems? What's the approach? Where's the metaphysics that goes into this question of quantization of space? Because in my view, this problem has not been solved. You have experimental evidence which indicates that this idea of quantization of space, which, as I say, goes all the way back to Plato. And in fact, Heisenberg, in the very last piece he wrote, which was published after he dies, tries to invoke Plato and the five regular solids as the foundation for his idea of quantum mechanics.
Heisenberg?
Yeah, Werner Heisenberg. And he does this to try and distance himself somewhat from Niels Bohr. Because he says Bohr was educated, Bohr came to this idea in a different way than I came to this idea. Bohr was educated in the British system. And in the British system, you accept the ideas of Newton and absolute space and so forth. So he relied heavily on this probability theory. Whereas I came from, in the German school, we studied more Plato. And we're closer to the Platonic school, which has this idea of quantization in it, going back to Plato and the five regular solids.
Say it this explicitly?
Yeah. So this problem has not been solved, right? So how do we approach this? Well, that's why the approach that I indicated in the pedagogy was looking at how Gauss looks at this question of the arithmetic geometric mean. Because what Gauss is talking about with the arithmetic geometric mean is precisely a example of what you were doing with when you're working through the disquisitions, is the idea of a concept of a quantized physical space. Yeah. That's what you have. You know, when you have a modulus, what it is in a certain sense you're quantizing the physical action. Because you have a modulus 5, then things happen in units of 5. Right? They don't happen in units of 3. They don't happen in. There's a cycle which comes back around every 5. But you have what you have. That's why you have to get into the book 3, and book 4, where Gauss goes through the residues of powers and then the quadratic residues, and then you get into the biquadratic residues. And that's where you get into this thing. That's where you see that these kinds of moduli are not simply these simple moduli, but are but you get into these complex functions. Anyway, I don't know if people want to get into that. That might be something for digression. Well, you have to do more work on the disquisitions. You have to get into 3 and then 4, and you get to the residues of powers and the quadratic residues, and then you can understand the biquadratic residues. No, that's section 5.
Oh, that's it. No, sorry.
That's the quadratic forms. That gets you into the arithmetic geometric mean. But it's interesting when you look at this thing, what Gauss was doing with the arithmetic geometric mean, that this is something which dominated his entire life. He really looked at this question for his entire life. And he says in his later letters that he began to look at this in 1791, which would put him at 14 years old.
14.
That's what he says, yeah.
He was working with the best scientists at that time, right?
Well, he was at 14. He was still in the Collegium Carolinaeum, which was the equivalent of his high school. And he had a good teacher, Zimmermann, who was an associate of Kepler. But he was his curiosity exceeded that of anybody else in that educational system. So you can't really explain it that Gauss just happened to have a lot of good teachers. There's an element of genius there, right? Well, what's interesting is that what was this insight? Where was this coming from? Well, that you have to look at again from the standpoint of this idea of the Pythagoreans, and it becomes much more simple when you look at it that way. As he indicated in the letter that I quoted, the 1808 letter to Schumacher, where Gauss says, we can now handle the circular and exponential functions as simple as 1 times 1. But there's a whole body of functions that are virtually terra incognita. And again, you see this question of the quantization of space, which you already know from looking at the doubling of the square and the doubling of the cube, right? That to double this, that there's a continuous, you can find a continuous manifold of one mean between two extremes. But you can never double the cube within that manifold. You can never double the cube by trying to find one mean between two extremes. You have to find two. But you cannot find two means between two extremes by first finding one and then figuring out where the other one is. Right? You can do that if you take one mean between two extremes and you build up. You go 1, 2, 4, 8. Well, now you have two means between 1 and 8. But the problem comes trying to find two means between 1 and 2. Right? Then you have then that produces the difficulty. But the difficulty is but then you go to the Architas construction, and you see in the Architas construction it's a continuous process. You can produce two means between any two extremes using the Architas construction continuously. But there's no continuous way to go from the process which generates one mean between two extremes to the one that generates two. Any more than there's no continuous way to change from a surface to a volume. There's nothing in between the surface and the volume. Yeah. I'm saying that it's continuous within each given domain. That is, if you take the is there something to erase it with? Right? If you can move this point P along this circle here, and that produces a continuous change in the proportions of those, of which this line cuts these two, which then gives you a continuous transformation of generating one mean between two extremes. But you cannot generate two means between two extremes using this process. For that, you have to go to the Architas construction, which means instead of just rotating this circle, rotating this point on this circle, you have to rotate the circle. And that generates the torus and the cylinder at the same time. Right? So you either have that circle not moving, or you have that circle moving. And when the circle's moving, it's also not moving. Because, yeah, right? It's doing the same thing as if it were not moving, but it's also moving. So it's doing two things at once. So you've added another thing. So it's a discrete change, right? It's happened. In other words, you're not generating 1.5 means between two extremes. You don't generate 1 1/3 means between two extremes. This is absurd, right? You're either generating one or two.
So it's a discrete change, but this discrete change causes two continuous.
You get a continuity of action, but the continuity of actions are ordered in discrete steps. And that's the way you have to approach this question quantization of space. That's the kind of functions which we have to look for. Right. So then you get what Gauss does with the arithmetic geometric mean. He's looking at this question of the elliptical functions. Well, or taken you then you get the next level is Leibniz's distinction that there's a still higher principle, right, which is the idea which comes off of Cousins of the idea of a transcendental function, which is higher than the algebraic functions. But as you know from the work you've done on the fundamental theorem of algebra, you have, in principle, the circular functions are transcendental. But in special cases, there's an algebraic relationship among the transcendental functions, like when you double an angle. There's an algebraic relationship between the sine and the cosine of the angle and the doubled angle, and the tripled angle and the quadrupled angle, and the angle which increases 100 times or by 1/100th of a time, right? So in effect, you could take whatever discrete steps you want, and you get an algebraic relationship. But the principle which produces those algebraic relationships is outside those relationships, is a transcendental function. And that gives you the circular functions. Then you look at what Leibniz did with the catenary. In the catenary, you have another puzzling thing, because you have these two transcendental functions, these two exponential functions, and the catenary is the arithmetic mean, is an arithmetic relationship between two curves that can never be expressed in the domain of arithmetic. And then you get this catenary function. Now Leibniz is looking at the question of the elliptical functions. And in the elliptical motion, he talks about how this is a harmonic relationship. He calls it harmonic motion because as the planet is moving around the ellipse, the angle is changing, which is geometric, but the speed is increasing constantly, which is arithmetic, but the distance to the sun is decreasing, it's changing inversely to the arithmetic, which is the harmonic. So he calls that harmonic motion. So there's two things happening, two transcendental actions happening in these elliptical motions. And what Gauss keeps calling the arithmetic geometric mean is a new transcendental. So it's not the algorithm that calculates the arithmetic geometric mean. That is the arithmetic geometric mean. The algorithm is sort of a just a way to calculate what he calls a new transcendental. Now, the idea of the thing that he shows with this arithmetic geometry expresses, and as I pointed out, this little quote from him in his fragments, where he says, for those who know nothing about the sublime and universal truths, there are practical applications of this, and I'll show them to you. Right? In other words, the physical universe itself, if you want to figure out how the physical universe works, you have to apply metaphysical principles to it, as Leibniz points out. If you want to understand how a pendulum works, you have to understand metaphysical principle. If you want to understand how a planet works, you have to understand this metaphysical principle. Right? But Gauss points out that the the practical application is not the principle. Right? The practical application is simply the effect. And the principle he's looking at here is the principle of the arithmetic geometric mean. So on the first level, we have the examples which I can go over this again in more detail if people want. But there's my there's two ellipses in which the shape of those two ellipses is quite different. And the way they're related to each other is that the ellipse on the right, the major, semi-major axis of that ellipse is the arithmetic mean between the semi-major and semi-minor axis of the ellipse on the left, and the minor axis of the one on the right is the geometric mean of the two axes of the one on the left.
You said it again?
Okay. Well, let's go back. Oh, it's better to look at them two together. Okay. So, this ellipse here on the right, the semi-major axis here, is the arithmetic mean of this semi-major axis and the semi-minor axis of this ellipse. And the semi-minor axis, which is not drawn on here, is the geometric mean between these same two axes. Okay, so that's the relationship between these two ellipses. They look pretty different, right? The one on the right looks almost like a circle. The one on the left looks different.
Did you choose the one on the left? Did you choose an arbitrary ellipse?
Yeah, I one that you could see that it was an ellipse. So here you see now that this changing motion, and this changing motion, you see as in both cases, as the radial line, that green line, rotates around, it gets longer and shorter. Now the amount that it gets longer and shorter in the one on the right is a lot less than the variation in the length of the one on the left. But if you take the mean length, it's the same. And the same is true with this ellipse. The one on the right, the one on the left is actually the first one I showed you, but it's real small compared to that one. This small and skinny one. But this ellipse is the major, semi-major axis and semi-minor axis are in the relationship of the arithmetic geometric mean to the axes of that ellipse. Oops.
Say the average length
Yeah,
in both of those
is exactly the same. Yeah.
I have a question. Even when we looked at this the first go round, I can never tell if at the way you have the two ellipse, well, the ellipse relationship to the circles and the way that it's placed, is it like perpendicular and like we were looking at it like a
No.
side?
No. They're
Which way? Where's the plane?
they're all in the same plane. The plane of the
They're all in the
screen.
same
Yeah.
plane.
The plane of the screen. And here are my charts which sort of compute that average length. And they're all the same. But if you take any except for quarter turns, they're also the same each quarter. But if you take within the quarter, the average length is much different. Right? Then you take an ellipse which is these ellipses look closer to each other, right, in shape. It looks like the one on the right is just a little bit bigger, right? But the average length of these two ellipses is completely different than the average length of the other. There they are compared. So what you have in this is you have for each ellipse, for each arithmetic geometric mean, you have a infinite but discrete series of ellipses which all have one thing in common. they all have the same arithmetic geometric mean. Right? Now, but what Gauss points out is that when you take the arithmetic geometric mean, there's a positive and a negative value for the geometric mean each time. Because the geometric mean is a question of rotation. And as Gauss points out in the biquadratic residues, that rotation is different than extension because there's two directions. It has within it two directions. If you have a line, and you have 2 points on the line, A and B, there's only one pathway to go from A to B. The reverse is going from B to A, right? But if you have a circle, and you have 2 points, A and B, there are two pathways to go from A to B, clockwise and counterclockwise. Because the line is unbounded, the circle is bounded. Okay? So, what Gauss says is that, well, this ellipse is just like, it's just on a line.
I'm sorry. Why is that a causal reason? That because the circle is bounded, that's why it has two pathways?
Because since it's bounded, you go from A to B this way, but you can also go the other way.
Okay, then why is because the line has no
Well, because if you go in this direction, you'll never come back to B. Because it's unbounded. It's not closed. So if you start here and you go in this direction, you'll never get to A. The only way to go from A to B is in this region between A and B. Another way to think about it is that in this domain, between has two meanings. Whereas in this domain, between has only one meaning.
You get more possibilities of boundary.
Yeah, that's right. Which is exactly the opposite of the idea of a Euclidean absolute space in which anything can happen. You actually have less possibility of things happening if you say anything can happen. Because if you say anything can happen, nothing will. So yeah.
I have one more question for you after the next segment. I'm waiting on some books, but have we ever looked at the case that in this, what we, I guess what we call it in this discrete moment, that in the small it may be continuous motions, but that we just maybe the way we're looking at it is wrong?
Sure, the way we're looking at it's wrong, but the point is you don't have discrete or continuity. You have this relationship between discreteness and continuity. This is the sophistry in the Copenhagen interpretation. You actually don't have discreteness, and you don't have to choose between one of the two. The universe produces both. That's why you get the quantization of space-time. And the point is that it's not that these small discrete things make up the universe. The universe makes up these small discrete things. The universe as a whole produces this change in the very small. It's not that the change in the very small builds up the whole. You build up the whole universe from the change in the very small. You get the small from the very large, from the universe as a whole. It's a universal principle. Because you don't have, what you have is you can't, if you keep dividing space as you divide physical matter, as you divide matter, you change it. Right? When you split a uranium atom, you change it into two other substances which make something completely different. You don't get a continuous change that if you just keep, you take a big chunk of uranium and you divide it in half, you get two chunks of uranium. And you divide each one of those chunks in half, you get four chunks of uranium. And you divide it in half, you divide it in half, you divide it in half. And you're still getting the same thing. But at a certain point, if you keep dividing, you start getting something new. Yeah. Yeah. Yeah.
Okay, so well, I don't understand why that's not continuous, because doesn't it kind of like not grow? I mean, obviously it doesn't grow, but doesn't it like?
Yeah, it does. But every little flake, every little flake of snow has 6 points on it. You don't have snowflakes with 5 points or 3 points or 2 points.
Like, it's a continuous
Yeah,
development, right? Or even when you have
What do you mean a
like,
continuous development?
well, even if you have like a mineral or something, where you see these like rock formations.
The crystals.
Yeah, crystals. They don't. They. I don't know how they grow. So.
Yeah, but they grow in discrete steps. They don't grow. It's not like they don't form out of a. It's not like a liquid.
Yeah, but it's not. Is it like?
I like a homogeneous liquid. Yeah. Yeah, sure. Yeah.
Even when you make rock candy.
Well, sure. Rock candy. What do you get? You get crystals. The sugar crystallizes.
Yeah, but why?
When the sugar is in solution,
Right.
then it's a homogeneous solution. It's not. It's a more like a continuous thing, but it's not continuous because the sugar may be dissolved, but the sugar, but it's a homogeneous solution. It appears continuous. Yeah, it's more like a blob. Huh? How does what? Well, the water from the clouds freezes and melts as it comes down. And out of that process, while it's freezing and melting and so forth, the water crystallizes, yeah. You think it comes out of the clouds that way? Yeah, there are a bunch of little elves up there who sort of put it together.
Isn't it condensation though? Is it condensation or is that going up?
Well, you condenses in the water vapor condenses into the clouds, and the clouds then, as they become condensed, the water condenses out of the clouds into water droplets, and as the water drops through the atmosphere, if it's cold enough, it'll freeze and melt as it comes down and form these crystals.
What if it's really cold up in the park? You get hail. You get hail?
Well, sometimes you get freezing rain.
But snow is water when you use the cloud.
Yeah. It doesn't precipitate out as ice. Ice. It changes its state as it goes down, back and forth. It goes through.
You think that like different atmospheric pressures then cause different formations.
Yeah, it does.
Snowflake, it does.
But they all have 6 points.
And is that related to the structure of hydrogen and oxygen?
Yeah.
Do they have similar?
Yeah, but see, but that's the point. When you have water, which is hydrogen and oxygen, but it's in different forms. When it's in water ice, which is crystallized ice, or non-crystallized water, like they're finding on some of these planets, the moons and stuff. They're finding ice, which is not crystallized that we're used to. We're used to crystallized ice on Earth. Huh? Well, it's more like it's sort of a slush type effect. No, it's because of the conditions that you get these different conditions.
But
It's cold. It's a lot colder.
It doesn't seem like the cause for that shape is even in the water itself, but it also doesn't seem like it's in the atmosphere.
No, it's not. It's in the interaction of several principles which produce this relationship. But when you look at crystals, for example, rock candy crystals, right, or mineral crystals, these crystals reflect the underlying structure, molecular structure. The macroscopic shape of the crystals reflects the underlying molecular structure of the. Right, but you don't find crystals. They all are 4 or 6 or 8. What you don't find is pentagonal crystals, except with respect to living processes. Although there's some, in certain high temperature artificial processes, they've been able to make quasi crystals, which are pentagonal symmetry. Go to there's a very good gem and crystal exhibit at the Museum of Natural History. Are you sure? Okay. There's a good one in Houston at the Museum of Natural History there. They have one real big, real extensive crystal. No. You don't have a big exhibit there. So all those people who are going to come down and campaign for Keisha's campaign can see them. Yeah, Michelle.
Okay. So, if bounded geometry gives you no possibilities, then why is you saying finite and unbounded?
Self-bounded.
That's right. Well, he was saying unbounded.
Well, that's what Einstein says.
Self-bounded.
That's what Einstein says, right? And there's not, the only distinction between Lin and Einstein is not in the form, but in Lin's inclusion of the idea of self-bounded because of the sort of higher epistemological idea of what we mean by universe. When Einstein was talking about the universe, he was referring, his concept did not take into account the idea of cognition and as an active principle in the universe. He was thinking about it more as a abiotic process. But Einstein's idea was that which comes out of Riemann, who says in the habilitation paper, right, that if space has any curvature whatsoever, it has to be finite. But its finiteness does not presume boundedness. And the problem people have with this is to try and come up with a visual image of a finite but unbounded. You know, the visual image which they usually use in popular expressions is, say, of a balloon, the surface of a sphere which is constantly expanding, right? But that's a really bad one because that doesn't really get the idea of unboundedness. The idea of unboundedness is more from what we were talking about earlier, from the standpoint of the difference between thinking of perfection as a fixed state versus the idea of perfectibility, self-perfectibility. Because if you have the idea of self-perfectibility, then you have the idea of an unbounded, right? But it's finite in the sense that it's not. It can only be perfected according to the mastery of certain principles. It can't be perfected by simply doing anything, which is why Rohatyn can never perfect the universe. But the universe can perfect itself by chewing up and spitting out Rohatyn. Right? The oligarchy can never win. Right? And the universe is perfect. It can perfect itself because it can purge itself of the. But of course, that is a very disruptive process. Can be very disruptive. It's better to do it orderly. Yeah, Nico.
At this whole development about
Yeah, well, think about how the physical economy develops. Think about the change. Think about a new discovery of a new idea, revolutionary discovery, as opposed to just the rediscovery of a new idea, like Kepler's discovery of universal gravitation. The revolutionary discovery. That's a quantized effect, because you have the universe in a certain state in which gravity exists, but human knowledge of man's knowledge of that is not correct, or is limited to a certain understanding of it. Kepler makes a discovery of principle of universal gravitation, elaborates the discovery and communicates it. Now that's a quantized change in the fourth domain, because gravity has gone from something which existed but was not really capable of being mastered by man to something that has been now under human cognition, now under human control, right? So we've mastered a principle which previously existed but was undiscovered. Call it undiscovered. That change occurred as a unique discovery inside an individual human mind. It didn't occur in the collective unconsciousness of the zeitgeist. It occurred in a discrete person who was born at a particular time and who died at a particular time and who lived in a particular time, right? And so you had a shift, a quantized effect, which changed the entire relationships of the universe, because it changed it didn't just introduce a new discovery, but it forced a change in the way human beings thought about themselves and had to relate to themselves, because they were no longer relating to themselves in a universe in which was governed by a principle that they did not understand. Now it was governed by a principle that they not only understood or were capable of understanding, but the fact that it had been discovered demonstrated something about a capability of the principle of discovery of all human beings, right? So it demonstrated a power of the mind which previously existed but hadn't been demonstrated to have existed in that way. And so with that demonstration you have a quantized effect. And that's how human progress occurs. That's how progress of the physical economy occurs. It doesn't occur in some type of continuity of development. You remember Lynn had this polemic one time about how, when you look at the history of mankind, there's a continuous effort of mankind to try and solve some of these epistemological problems. It's not that everybody everywhere is always working on it, right? But mankind as a whole is always working on it. But the way mankind as a whole is always working on it is through individual creative discoveries, which also occur in a quantized effect, as we've all experienced, like even from the earliest one, the discovery, the doubling of the square. You're sitting there looking at the square, you got all the information you need. No amount of information is going to help you, except to know the answer. And if somebody gives you the answer, then you still don't know the answer until you discover it for yourself. When you make that discovery, you're changed. You're no longer the same person you were. And in that respect, the universe has changed, because the universe used to have you in it without this knowledge, not only of the principle, but of your ability to discover the principle. And now the universe has you in it with the knowledge of that capability of your own mind, which then you go out and educate and talk to other people, and the universe has the capability of creating a renaissance, of changing other minds, right? So that capacity of the universe to develop in that way is a function of discrete transformations. Now, if you were to look at those discrete transformations from the standpoint of a mathematical algebra, you would say they're random. how can you predict who's going to make the discovery and who isn't? Right? How can you predict when people are going to make the discovery? How can you predict out of a room of, out of a population of 6.2 billion people, how many of those 6.2 billion people and when are going to discover the principle to double the square? Right? I mean, think of it like an atom, right? Like you were looking at an atomic structure. You're trying to predict when is a neutron going to come flying out of this atom, right? It would appear to be a totally random process, but it's not a totally random process. It's a totally deliberate process, which is capable of becoming which man is capable of becoming increasingly master of, even though you can never force somebody or do anything that could predict how that person is going to make a discovery. As you know from your own experience in organizing, right? You can organize somebody and one person will respond a certain way and another person will respond in a completely different way. Right? And you can never predict in a linear way what's going to organize one person versus another. But you can predict that you have the capability to organize everybody if you could just figure out what it is. Right? Everybody's organizable. So that's where this question, that's another example of how to look at this question of quantization and the foolishness of thinking of this as a random process.
This whole thing about like with atoms and stuff like that, how because I was reading some things like Jonathan Tannenbaum talking about Mendeleev, and he's describing how I guess the theory that some scientists have is that you split the atom and you split the say there's water and hydrogen and oxygen, and then you split like little little hard bodies that hit against each other or something. And then it splits it, and it keeps on doing that until you get to a point where it doesn't do that anymore.
Right.
And then he's saying, well, that doesn't really happen because you can keep going or some process.
Yeah.
But I don't understand. Like, what is like the atom? What is it? Like, how do you?
Well, that's the point he's making there. That's the polemic he's making. What is the atom? Right? It's the atom. What we call atoms. Atomic structures are really the anomalies in the macroscopic domain, which we explain as a microscopic effect of an atomic type structure, of something which has a certain integrity to it on the microscopic domain. No one's ever seen an atom directly, right? You measure, you see the effect. You see, you discharge, you put an electric spark in a cloud chamber, and you see tracks, which indicate the existence of particles that are moving in that cloud chamber. And the cloud chamber is just sort of vapor, sort of going around, and you put a spark into it, and you see tracks in the vapor. You can take a picture and see the tracks in the vapor, right? And if you put a positive or negative electric field around it, you can deflect those tracks in a certain direction, which indicates that those tracks are negatively charged or positively charged, depending on how they're deflected by a negative or positively charged field. So then you say, well, these are negatively charged particles. And we call these negatively charged particles electrons. We give them a name. These are the kinds of experimental evidence but when you can't say that, okay, we have one proton and electron, and that's hydrogen, and we have oxygen, and we put the two together and we get water, which is simply just the sum total of the protons, electrons, and neutrons in hydrogen and oxygen. Because obviously water is a completely different characteristic. The protons, neutrons, electrons in water are in a different relationship to each other than they are in oxygen and hydrogen independently. Right? So that's what I mean by it's not that the universe is built up from these small particles. It's the universe as a whole produces these. Well, you got to start to understand the very small. You have to start with the whole universe. You don't understand the universe from the very small. Huh? Yeah. But it's also the way. It's also what Leibniz is dealing with the calculus, right? They take the catenary principle, right? You got this chain which has an overall effect. So every small part, whatever it's doing in every small part, is the effect of the whole chain, right? So what you have to look at in the calculus is not what's happening in the small, but what's the relationship? How does the whole thing, how does the universe of the chain, how does the total action of the chain express itself in the small? And how from that small expression do you determine the whole thing? Just like Gauss determining the orbit of Ceres. You get this little piece. Well, what do you know about that little piece? You know that that little piece exists in the solar system. And you know that that solar system is governed by certain principles. And you say, okay, how would all the principles of the solar system express itself in that little piece? And that's how Gauss determined the orbit of Ceres when everybody else couldn't, because everybody else was saying, okay, let me take this little piece and I add another piece to it, another piece to it, another piece to it, another piece to it. Right?
Yeah, it's just a method of thinking.
Yeah, exactly. That's why we study this idea of science, because this is the method of thinking that's necessary to rebuild the economy. It's the method of thinking that's necessary to change the political situation. You have to get people. We have to educate people to think in this way. That's what people don't think about. They think about the little things, right? They say, well, the effect of the economic collapse is that my credit card debt is going up. So if I can figure out a way to refinance my credit card debt by the rising value of my house, right, then I've solved the economic problem for me, right? But they're not thinking about the fact that their credit card debt is going up and their house value is going up because the economy is collapsing. So even if they do something in the small to affect that situation, whatever they do is completely futile because the whole system is coming down. That's what's causing these things. That's what's causing their life to be organized the way it's organized. And they're not looking at the big picture. They're not looking at the whole. And we have to get them to look at it. Yeah, Michelle. Okay, then Jenny. Yeah.
Is quantization of space related to the idea of potential?
Yeah. Yeah, sure. I mean, that's, the in the sense that it's a potential, but it's not. It's sort of it's sort of a further development of what Gauss is talking about with potential, because you get a change in the potential, right? A discontinuous change in the potential.
And like what I was thinking, I was actually thinking about it. I don't know why. I was just thinking about the other day. When you're dealing with chemistry, you can't just put two things together and assume you're going to get a reaction
Exactly.
out of it. You have to have a certain threshold of energy for the chemicals to become reactive.
Mm-hmm.
And once it attains that threshold, then you can have a reaction take place and you have something that's more stable.
Right. The same thing with atomic processes. You can have neutrons come out of nuclei, but if you try and put a stream of neutrons into a nucleus is not so easy. Yeah, Jenny.
Well, I was thinking about the thing you said at the beginning about how people you're talking about how a physical process created the universe. You're talking about the floating plasma disk.
Right.
And I was thinking about and then how the planets were spaced like harmonically.
Right.
What played like what May talked about
Mm-hmm.
with the harmonic division.
Right.
So, because in that section of Maus, it talks about the combining together of same difference in
Right,
essence,
right.
and they have to be forced together. Is that? I mean, because and then later you talk. I don't know. It's the
Yeah.
idea of like this physical process.
Exactly.
Because that kind of implies a physical process
Right.
that creates. Because I couldn't think of what else. Because he makes it very explicit, like they're forced together. It's
Yeah.
kind of a funny idea.
Yeah. Yeah, because in other words, there's a directionality to the universe, right? There's an intention to the universe. Things just don't sort of come together in an amorphous way. They actually have to be, just like creative ideas have to be forced. They don't just pop out of you, right? You have to do a lot of work. You have to force these anomalies together. If you don't force it, if you don't do the work, if you don't put the effort into it, that's where passion comes in. If you don't do that, then the creative idea doesn't happen. So people sit there and say, I don't know why I can't get it. That's called blocking. What are you blocking? You're blocking the force. You're blocking the passion that's going to make the idea come out, right? That's sort of what Plato is getting at there. In a sense, that's the way the creative process works. Right? And people complain about that. That's what Leibniz was reacting to, because people complain about it. Well, if this is the best of all possible worlds, right? Why do I have to work so hard to think? But that makes it the best of all possible worlds, right? Because if you didn't have to work at it, it would never be creative. You wouldn't. Yeah, Tim.
Just correct me if I'm wrong. According to Newton, it's the characteristics of the planet that determines the orbit, right?
More or less,
Mass,
yeah.
velocity.
Right.
While according to Kepler, it's the orbits that determine
Right. Exactly.
the planet. So, but are these orbits? Because I can see how someone could maybe like become a bit too fundamental, like fundamentalist with the idea of like orbits like harmonically fixed. Isn't there a certain element that would depend upon the characteristics of, say, the initial, like say the spin from a disk? Wouldn't
Sure.
the spacing of the orbits, like maybe they're all harmonically? I'm thinking of like an accordion, right? Like
Right.
the greater the disk, the greater the spin, you know, the greater the.
Sure, all those characteristics came into all the characteristics of that spinning plasma disk affected the outcome that we now call the solar system.
Yeah, because I was thinking, I mean,
But then
we
the
can create. I mean, because you think about NASA scientists and these engineers, how they do it, it's quite remarkable the fact that they can sling a man-made device across the solar system, and in fact, we're creating an orbit.
exactly. But we have to do that within. We still have to follow the same.
They
principle.
always had to fly in parabolas.
Right.
Yeah, they have to arc them. But it just seems that, it's not like, because if you take the ancient view of these crystal orbs, the fixed
Right.
spheres, the fear of like piercing through and breaking one of them.
Right.
Right? It's not that fixed. It's not.
Well, that's what Tycho. No, but it's fixed. It's not fixed. It's It's not fixed, and that's the argument. See, that's the sophistry that the Copenhagen interpretation brings in, because they say, if you say that the universe depends on principles, then ultimately you're saying it's fixed. And therefore, if you don't say that there's randomness in the small, then you're saying that that nothing can change. That if you take the principle of change and you extend it to the very small, you end up with randomness. And that's their argument. If you look at those discussions between Born and Einstein, what Einstein's objection is to Born is that he's a positivist, and Born's objection to Einstein is, well, you're a determinist, because you're saying if there's an ultimate set of rules, set of physical laws, then that means that everything is predetermined. And Einstein's saying, no, that's not what I'm saying. I'm saying there's still a higher principle. But Einstein is not able to really deal with that question because Einstein did not really understand this principle of cognition in the way Lynn does. Because what you just described is what man does with these spacecraft. That is changing the orbits in the solar system. We're creating orbits which were not there. Right? So the solar system did change its laws, because before man started sending objects out into the solar system, the orbits that existed were the remnants of that spinning plasma disk. Now we're creating orbits
It's just
which weren't there.
The paradox in my mind, though, is that the engineers are, in order to, because in a sense, it's almost like they're creating an orbit.
Yeah.
Although every orbit has to follow a convection.
Right, but they're creating orbits which weren't there.
But the way they're doing it seems to me by varying the mass and the velocity of the spacecraft involved. So
Well, they're not varying the. They use the velocity. Yeah.
Yeah.
Sure.
Don't they use other planets?
Sure. That's what they have to do, because it would take too much power to fuel. So they do those. That's why if they want to go to Jupiter, they first go to Saturn. I mean, to Venus. And they go. If they want to go to Jupiter, they first go to Venus. They go by Venus and swing around.
Whoa. It's so funny because
Yeah.
you had to factor
Why
at
is
the same
that?
time.
Huh?
Don't you have to factor at the same time the decreasing weight of the shuttle because you're expending fuel?
Oh, but we're talking about very small spacecraft that go out there, so the amount of weight. No, they don't. They don't have much fuel on them. That's why you want to. A few of them have atomic reactors on them to fuel them. But they're very light, the ones that go up there. So there's not a big change in the mass.
So does that new orbit of the spacecraft alter the harmonics in the planetary orbits?
Well, in a sense, yeah. It's like it's like a grace note in a piece of music, right? It alters the whole. Well, look at the Opus 33, number 3 of Haydn, right? The bird, the Vogel, right? And the F sharp is in the grace note, right? So this little grace note, which is the little chirping of the bird, is actually the Lydian interval there.
I didn't get some of these examples of the
Spectroscopy? Spectroscopy. Yeah.
So the discontinuity was that it's changing colors, but it's like at a particular intensity that it changes?
No, what happens is that if you take at any given temperature, it's actually radiating all the colors. But one of the colors it's radiating with a greater intensity. So when it's glowing red, it's also emitting yellow and orange and blue and violet and so forth. But those are higher frequencies. And so it's emitting those, whatever it's emitting of those frequencies, it's emitting with less intensity. So that's why it looks red. And then as you increase the temperature, it starts to glow more orange, and then maybe yellow, right? So it goes up the rainbow as you increase the temperature. And as you do that, the color, the reason why it's changing color, it's still emitting all the frequencies, but it's emitting one of them at greater intensity.
Why does the color change as it changes? Why?
Well, that was one of the things that, because well, Planck made an assumption that what you have, that you have to treat the atoms of this material as harmonic oscillators, oscillating back and forth, and that they're emitting light as a result. And that as you increase the temperature, the oscillations are increasing in frequency. And increasing heat increases the frequency of the oscillations. And that's not a physical hypothesis of his. That's an assumption that he brings in order to give a physical expression to his experimentally empirical determined results.
Based off of another,
Based off of measuring the relationship of the color spectrum to the temperature of the body.
But if all of the colors are being radiated, doesn't that mean that there's several different frequencies?
Yeah, all the frequencies are being emitted. What you're looking at is the one that's the most intense.
Oh, hey, that's like Adam was just describing how they do one of these cell phone networks. One of the technologies
Yeah.
is like one is like this kind of like cheat method where everyone just talks and like everyone waits to talk, but
Right.
so the intervals are so short,
Right.
you can barely hear a difference.
Right.
And the other one is everyone's talking in the room, but each frequency is like encoded at with a different encoding, and you get the so the conversation has the key to
Right.
decode it,
Right.
but like they're all going on at the same time. So you just mean the one that has like the greatest frequency, or the
Yeah, the greatest amplitude.
like the height?
Well, that's if you're thinking about them as wave. But what you're measuring is basically you're taking the visible light. You're basically putting it through a prism and looking at the frequencies that are coming out.
Isn't that how they would have to measure the
Yeah.
It's just funny.
That's how they measure it.
Yeah, to measure the intensity kind of is both. They have to take both sides of the paradox.
Yeah.
To do it, like they have to measure it according to the idea of it being a wave, but they're investigating the phenomenon of it acting as a particle.
Well, that's why Planck himself said this is a real paradoxical idea. It wasn't until, nobody thought of thinking of these things as quantized effects before Planck. And Planck's approach to it was not as to say that this was an actual physical effect. That was basically Einstein was the first one to really say that this was actually, that physically it's quantized. But then once you say physically it's quantized, then you have the problem of how do you explain that sometimes it appears not quantized. So that's where Bohr's complementarity principle was. It's neither a wave nor a particle. It's a wave when the experiment shows it's a wave, and it's a particle when the experiment shows it's a particle. But when you're not experimenting on it, it's neither wave nor particle. It's both.
What is that, like quantum theory?
Yeah. That's the Copenhagen interpretation of
Yeah, I have
quantum
I
mechanics.
have a book at home where it has the cat in the box.
Schrödinger cat.
Yeah, yeah.
That's a similar type of thing.
Probability of the cat being.
It's not the probability. The cat is either dead or alive. But until you look, it's
You
neither.
don't know.
No, it's not that you don't know.
What?
The cat is neither dead nor alive until you look.
It's a mishmash of both.
It's neither one. Right? It's not that it's dead or alive. It's neither dead nor alive. Yeah, it's the Parmenides paradox. But the reason, see, the point I've always made about this is the reason why this came about has nothing to do with the physics. It has to do with the what was going on in the 20th century. It reflects this pessimism in the 20th century, this existentialism, that there's somehow this indifference to human thought. And so therefore, you come up with this paradox, and your solution to it is to say, well, all we really know of the universe is what we perceive. And what the universe is doing when we don't perceive it is a matter of speculation, but not a matter of science. It's Kant's idea of phenomenon versus phenomena. That is, the thing in itself you can never know. What you know is the way it's perceived and what your mind does with the way it's perceived, and so on and so forth. Right? That's their, which is the same thing as Aristotle. And Ptolemy says in the beginning of the Almagest, I agree with Aristotle. You can't know anything about the physical world because the physical world is governed by processes you can't see. So since you can't see them, you can speculate about them. That's the domain of metaphysics. That's metaphysics, speculating about causes. But physics is just describing what you see. So if you define science, just like with economics, if you define economics to be money, then you can come up with all kinds of things like supply and demand and all this other stuff. But you have to first say economics is money. Once you say economics is money, then you've eliminated the reality from economics because money is controlled by the people who make the money. Right? It's not a physical process, it's a political process. So once you that's how sophistry works. Sophistry doesn't work by getting people to accept all your arguments. Sophistry is getting people to accept the terms of the debate. That's what you run into all the time when you're organizing here in D.C., right?
Don't get framed.
People want don't get framed. People want to set the debate according to certain terms. And we come in and we say, no, we're not going to set the debate on certain terms, and they object to it. And we keep objecting to their objection. And sooner or later they realize we're right?
And then they hold their meeting somewhere else.
Then they leave the microphone.
Well, they know that doesn't work because they can't seem to get rid of us. There's nothing they can do, The point is, they can insist that, if you don't accept the terms of the debate, to frame the debate the way they want, they're just exclude you. That's what they ultimately do. Oh, we just exclude you, right? And we said, you exclude us, we include you in. So they can't get rid of us, right? They can't win because the most they can do is pretend to exclude us. But that's impossible because we don't accept that. Unless we decide to exclude ourselves, right? Unless we say, oh, well, since we don't fit in, since you're not going to accept us on your terms, we'll just go home. Like the poor schnook in that office who thinks he can avoid you. You got the whole state of Texas on his case. That's what. Yeah, it's the same thing. You have to be a constituent, right? Which is a complete bullshit because you're right. He meets with all kinds of people. Yeah.
I think the discontinuity of the changing of the lines in spectroscopy
Mm-hmm.
was, like, how are they changing? How are the lines changing for the different elements that they saw the
The frequency of the lowest line in the X-ray spectrum changes with each element.
So the left, where it is located?
Yeah.
Okay.
The frequency of the lowest...
Okay, and so for sometimes in reverse, it wouldn't go in order.
No. What I'm saying is that in Mendeleev's chart, he ordered elements according to... He looked at the atomic weights of elements, and he grouped those elements according to their atomic weight and chemical properties. And that's how we got this periodicity, right? Because if you put them together, if you put the ones with the similar chemical properties in a column, and you put the atomic weights in a row, then the ones with similar chemical properties will line up in the same columns. You see a periodicity among these atomic weights and chemical properties. But there were a couple anomalies in there, like iodine and potassium. Yeah, where according to the atomic weight, they're in the wrong place with respect to their chemical properties.
Are those next to each other?
They're next to each other, right? But they're in the wrong column for their chemical properties. If you put them in the right column according to their atomic weight, which you get the atomic weight by turning them into a gas and measuring the weight, equal volumes at the same temperature, you can, you can determine the atomic weight. So you compare the atomic weights. You've got, if they're in the right order according to their atomic weights and in the wrong place, they should be reversed with respect to their chemical properties. If they're in the right order with respect to their chemical properties, then you have, I think it's potassium is the lighter one, ends up being in the heavier place. So that gets resolved when you order the elements according to the frequency of the lowest band, lowest frequency in the X-ray spectrum. And when you look at that, you get this idea of atomic number. And later, that idea of atomic number becomes associated with the proton.
Yeah. So it's reversed in the spectroscopy and in the other method of measuring?
No, it's then it gets in the right order in the spectroscopy. So that led to a reorganizing of the periodic table according not of atomic weight but atomic number.
The lowest band of the
X-ray spectrum. Mm-hmm. Measuring heating these things into a gas and then doing a spectroscopy in the X-ray, exposing a photographic plate that's sensitive to X-rays.
When they get the X-ray spectrum, it lines up.
Each element, yeah, it lines up according to atomic number. These are the experiments of Mosley. Hmm?
What was Mendeleev doing? Like, when you figured out that there was like...
Besides building railroads?
What?
Besides building railroads?
I didn't know he did that.
Oh yeah, he built the Trans-Siberian Railroad. or he organized. He was the minister of railways in Russia.
When he was actually trying to figure out the difference between the mass and the chemical elements.
The atomic weight, yeah,
Atomic weight
and the chemical properties, right. Like you take these inert gases which do not combine chemically, or you take things like chlorine and fluorine and so forth, which combine very readily with sodium and these other lithium and these other elements. Those kinds of chemical properties. I'm sorry, what?
How do you even know we have the gas?
How do you know we have what gas? Well, that's what chemistry is about, isolating these various elements.
Yeah, I guess a lot of it does.
Sure, it's not like one guy just the whole. It goes back to Lavoisier and all these works to try and isolate different elements. Lavoisier's the discovery of oxygen.
What year was it?
Lavoisier, he was he did his work in the late 18th century. He was executed by Robespierre. Well, yeah, I think he did too. But I think Lavoisier discovered yeah.
Wasn't it also the case, like, until Lavoisier, people didn't understand, people thought that some chemical reactions you just lose stuff?
Yeah.
It wasn't until Lavoisier proved that no, the whole idea that you always have, like, stuff doesn't disappear in
Right.
a chemical reaction.
Would you say that?
No. Yeah, well. Okay.
It kind of strikes me. It's kind of really. It seems like if it was Lavoisier, it took Lavoisier to determine that, which I think today we regard as sort of like a very, very basic tenet of discipline chemistry. It seems like it's one of the newer.
Sure, a lot of these things are new, but the problem is that the problem people don't. We should learn these things from the standpoint of their experimental evidence. Replicate the experiments of Lavoisier in his chemistry. That's what's missing. All right.